And welcome, Mindsetters, to this session of Grade 11 Learn Extra. I know you were in Grade 10 last year, now you're in Grade 11. So, you're adjusting, but that's why we're here. We're here to help you adjust and make it happen. Because it's Ty here, and I'm here with Tracy.
Yes.
Always lovely and bubbly, Tracy.
See, but that's what Tracy's are like, eh?
Both of you.
Do you see, we had a Tracy in Grade 10 last year. Now we have, I've been promoted with these Grade 10s. Do you see, I'm doing Grade 11 now. Cool. And now we have another Tracy. What can we say? We're good science teachers, eh?
Awesome stuffs. Yes, so what are we doing today?
Today we're going to look at investigating forces, and we're going to revise a little bit of what vectors are, what scalars are. We've got a bit of a demonstration. I have a challenge. It's not a challenge question, so there's no prizes for it.
Yeah, so
No, okay. But I have a challenge for the viewers, for the mindsetters, to make them think that they're grade 11, they've got to think a little bit out of the box. So
yeah, because they're used to being grade 10 where they're kind of like, we'll take care of you. Now in grade 11, you're like, haha, take care of you what?
Yeah.
Yes.
And it's a nice section. Look, I know they struggle with it, but I really like it.
Yeah, but
so
that's what we're here for. We're here to help clarify and make it work.
Absolutely.
So, while you make your way across the board. So, you grade 11s. I know you from last year. So you know the drill by now. You need to get on the page, www.facebook.com/learn extra. Chat to me. Let me know what you guys think. If you're lost in it, if you need help, post it on the page. I'll also be posting up the links to the notes. And if you want to go find them yourself, you can also go to www.mindset.co.za/learn/extra/live. So yes, make sure you go check that out. It's all updated for you guys. We're just like, what? They keep harassing us for like notes and stuff. Well, not harassing. You guys are well within your rights. So yes, we now have that all set up for you guys. So make sure you visit the page. But for now, we have a session to do. So Tracy, take it away.
Oh, thanks, Ty. Guys, really get on the page. I was showing my kids today, and lots of resources for you, and the notes are brilliant. Okay, just nice revision, nice summary, nice something for you to keep. Plus, the questions I'm going to do a little bit later on the notes, so that helps with the picture point of view, because this is very picture intensive, okay? So like I said earlier, we're going to look at investigating forces. Hopefully you've done some of this already. And what are we going to try to get through today? Okay, well, we're going to get through the concept of a vector, which you learned last year, and hopefully you've remembered. We're going to show you how to draw a free body diagram. That's a new concept, so you need to listen carefully, because it is different to a force diagram. And then we're going to use this little math thing that I know some of you hate. We are going to use trigonometry to find the resultant of two perpendicular forces, okay? So we're going to use a little bit of trig, we're going to do some scale diagrams. Hopefully you have a ruler, a pencil, and a protractor with you. If you don't have a protractor, that's okay, just follow me. But it's really important that you get one, and if possible, try and get one that is just 180 degrees and is the smaller of the, you get all these wonderful 360 ones and pretty colors. Try not to get one of those. Get a nice clear one that you can see all the numbers on, and that's only 180 degrees. Otherwise, you're going to get yourself into a lot of trouble, okay? So let's start off with revising some concepts, and that is, what is a vector? Okay, and you learned this last year. It's one of those things where we have a nice little definition. It says it's a physical quantity which has both magnitude. Remember, magnitude means that it has size. All right, so let's just remind ourselves that magnitude means that it has size and direction. So it's not just the case of something where the size is only important and its units, but where it's going. So examples of vectors are something like velocity. Now, we're going to deal with what a scalar is in a second, but velocity says to me that I can run at, and now I'm just dreaming, 3 kilometers. No, that's a bit slow. I can say run at 10 kilometers per hour. Okay, 10 kilometers per hour, but I'm going to run 10 kilometers per hour north. So I'm going to go in a specific direction, okay? So velocity is a vector. Force, which is what we're dealing with today, is a vector. Now, we defined force as a push of a pull in grade 8 and 9, and that's exactly what it is. It causes something to change motion. But now we need to know which direction. And in fact, that's the issue that we're going to really deal with today, is what is the direction? What is the result of forces acting on an object? Because up till now, we've really just made it only one force, maybe two forces acting in opposite directions, like in a tug of war, made it nice and easy. But now, We also know that in the real world, that's not going to happen. Okay, so we need to say what happens when we have forces acting in different directions. What's the result? What does it mean for us? Okay. Also, why force is a vector? Think about something that's related to force, which is weight. Okay, ladies, and I don't mean whether you weigh 60 kilograms or 100 kilograms. Okay, that's a terrible use of the word weigh. That's, sorry, weight, not weigh. There we go, let's make that a T. Often, this is the biggest problem we have, is we'll say to each other, oh, I need to lose some weight. No, you need to lose some mass. Okay, weight is a force. Weight represents the force that the earth attracts me with, or that the earth attracts you with. And weight always acts down, because the earth draws us to itself, okay? So we are always pulled towards the earth, okay? So force, weight, other vectors, acceleration, okay? That's gonna, you remember that from last year. This caused you a little bit of grief, I'm sure, because when you did acceleration, do you remember doing equations of motion? We didn't like acceleration, okay? Then I'm not saying it's the opposite, because it's not, but we have a scalar quantity, which is a physical quantity which has magnitude only. Easiest scalar is time. Time is measured in seconds, or minutes, or hours, or days, or years, but time only goes in one direction, despite the fact that sometimes you would like to go back in time. Wouldn't that be fun? Okay, but time can't go backwards, so time is a scalar. Mass is a scalar. Mass, which we measure in kilograms. How much matter does something have? That's a scalar, okay? Speed is a scalar. Speed as opposed to velocity. And most of the time when we're talking about velocity, we mean speed, because we're not concerned about the direction something's moving in, but we're talking about how fast it's going. So when we talk about Usain Bolt, who we know can run the 100 meters in 9-something seconds, we can look at his average speed, because we don't really care what direction he was going in a straight line, okay? Or we're traveling in a car and we say the speed limit on the motorway is 120 kilometers per hour. That doesn't mean you can only go at 120 kilometers per hour north. So if you're traveling north, then you can go 120 kilometers per hour, but if you're traveling east, then you can only go 80. That's just stupid. So it's 120 kilometers per hour regardless of direction, okay? We are going to concentrate today on force, okay? Now, so we can look at our vectors. How do we represent a vector? Now, you did this last year. We use an arrow. The arrow is very special. It's not just random and, oh, that's great. The arrow has two parts to it that are very important. Well, three. This part, which we call the tail, okay, it's the beginning part, and it's quite strange, but it's called the tail, okay, that's where the vector starts. So that is where we start everything, is with the tail, okay, so that's the beginning point. The head, which is where the arrow is, points in the direction, okay, so it has to have an arrow, and that arrow shows me direction. So it's quite important. So I can show the direction that the vector is going in. The length of the arrow, so this part, oh, that's terrible, but just pretend, represents, wow. Okay, guys, it's been a while since I've worked on this board, as you can all tell by the really terrible handwriting. So I'll write a little bit slower and hopefully it'll get better, because that's just horrific. Okay, so the length of the arrow represents the magnitude of the vector. Why is that important? Because when it comes to solving vector diagrams and representing vectors, we're going to start adding vectors together, okay? We're going to do it by an accurate scale diagram. That length is important. Okay, so that comes down to you being a little more exact than you're used to. So we all remember this from last year, you did a little bit of it. So, how do I add vectors? Well, what we have here is, if I can get it to actually do things for me, there we go, is we have two vectors, that, let's call these two forces, okay? So over here, we have a tree. So two people are trying to pull out a tree, and one says, okay, I'm going to pull at 5 newtons, and this person says, I'm going to pull at 7 newtons, and we want to go, okay, where's the tree going to go? Okay, well, hopefully, you guys all saying to me, well, Tracy, it's quite easy to actually tell that the tree is probably going to go off in that direction somewhere. Okay, so we got a roundabout idea of where it's going to go. That's fine. But how do we now take this and we say, okay, I want to actually represent this? We would need a little bit more information than what I've got on the board. And that can be a whole different, it depends on the direction. So say I tell you, and I know this looks like it's at 90 degrees, but it doesn't have to be, but let's say I tell you they're at 70 degrees to each other. Okay? So the one person's pulling off in this direction, the other one's pulling, and there's 70 degrees between them. So we go, okay, we can work with that, because now, if we draw a diagram, we're going to start with okay, we'll do that one, with the 5 Newton, okay? So here we go. And I can change its direction if I want a little bit, but let's try and keep it looking more like the original. So we go, okay, there's the 5. Now, if I'm doing this by scale diagram, I would choose a scale. So we would draw it and say 1 centimeter equals 1 Newton. So this line would then be 5 centimeters long. Then we go, okay, then we need to say, okay, well, now I've got to draw the next vector. They're at 70 degrees to each other. So we go, okay, I want to change the color. Let's do it here. Let's do it with one of these. And you would take just extend it a little bit in pencil. Then you take your protractor and you measure 70 degrees. And you go, fine, I got 70 degrees now. So I can now draw in my 10 Newton, which would be there. Okay, this is all by scale diagram. We're not doing anything by trig yet. Okay, so what we've done is we say this is our 5 Newton force. There's the 70 degrees, and this is my, 7 Newtons. So by scale, this would be 5 centimeters. That would be 7 centimeters. And then we go, okay, well, now I need the resultant. I'm just going to do this in another color because I want you to be able to see it. So let's do it in green. And we go, okay, there's the resultant. Oh, close. Sorry, it's just, it's been a while. Come on. And it's important to talk to your
to your equipment, so it's...
Or just delete it because it's just not doing what you want. Sure. It has been a while. There we go. So.
There we go.
There we go. That's as close as I'm going to get. It's just not quite working. That's why drawing it on paper is so much easier. Okay. Now, this is your resultant force. Now, you can see from my diagram, now I said it was going to go, if we look at my original, I said it was going to go sort of in that direction. It hasn't quite worked out that way, but I'm getting relatively the right value, okay? What we would then do, and we've done this head to tail because we've gone head to tail. Okay, so we've got heads and tails together. Remember with the resultant vector, it starts where your first vector started. Starts where the first vector started, ends where your last vector ended. You would then, okay, and I've made these numbers up as we've gone along, so I don't actually know what the answer would be. You would then measure this line, okay, and I'm looking at this and going, it'll probably be bigger than 7, I'm not sure, and you would measure this angle. And you would then be able to tell me exactly what the resultant is. So you would say to me, the resultant is 7.5 newtons at probably about 30 degrees to the 5 Newton force. Something like that, okay? I've made those numbers up, so don't quote me on that, please. Okay, you all understand where we're going. I know I've gone through this really quickly, because what we're going to do, okay, and I think, there we go, is after the break, really excited, I'm going to get some friends in, okay, to help me, and I'm going to show you another way of doing this, because two forces are easy. What happens when there's 3? Okay? And we're going to look at what a free body diagram is. So we're going to take a break, Ty, and then we're going to start playing with some stuff.
That sounds like so much fun. So mindsetters, make sure you don't disappear. And for those of you who remember from last year, like I always say, go do whatever you have to do. Go get some water or whatever you have to do. If your mom says go cut onions, you know I've got a thing against onions. But yes, just go, just do it. But make sure you come back because we're going to take a short break. See you soon. Haha. I'm sure you didn't expect this one. So guys, we're going to be starting off right from the beginning with an experiment. So pay attention, please. I'm not down here just for just. We need to pay attention. All right. Tracy?
Well, you are just because I like men at my feet, but that's besides the point. Anyway, so guys, what we're going to do now is we're going to look at what happens when we've got 3 forces on an object, and I have 2 wonderful happy helpers. And I've just got a little tin, I've put some weights in it so it doesn't go all over the place, and we're going to play a little bit of tug of war, okay? So we've got the 3, and we're going to just lift it quickly, okay? And we're going to see if we can, now if we all pull nicely, we put it off to the side, but it's okay, we're great, Mr. Wilson on the camera. And this is nice and stationary. Now, because I'm a girl, and I like to win everything, if I pull harder, it pulls towards me. Now we're going to pretend Ty is, he's a big, strong boy. So he's going to pull. Well, Ty, can't help it. Pull. Okay, but now it means now it's pulling more towards him. And now John is on the other side, and he can also pull. And we could be at this all day. But how do we know? You see, I'll just let them feel like they're winning. You see? How do we know which direction it's going to go in? Okay, because even though Ty's pulling towards himself, pull, Ty, pull, pull, pull.
Pulling.
It doesn't necessarily go to him because we can pull it so that they're all, now it's nice and stationary. This is actually nice and stationary. I could probably play my drums on there if I want to, but I won't. But if I let go a little bit, even though Ty's pulling and John's pulling, it's not going towards either one of them. It's sort of going in the middle. So we need to find a way of how to deal with this, okay? Now, I quite like the format at the moment, so we're going to put it flat, okay? And from here, we can draw a diagram. Now, if we had Newton meters on the side, if we had almost like weight meters, I meant to bring one, we could actually measure how much force we were pulling it at, but we're not going to worry too much about it. So what I'm going to do is I'm going to say, here's my first one. So we've got a line, it's not very straight. What you would do at home, and I would love you to do this at home, I think it's such a good experiment, is you would rather just draw a dot there and a dot there, and then you use a ruler. Okay, to actually take the 2, because my first line over here is not so good. And then we do it here, and we do another one there, and we realize that they all meet in the middle, okay? So what we're going to do is we're just going to, don't you want to just pull it tight for me, Ty? Because then I can use this as my guide.
Yes, and also as a note,
You see?
do this with paper and not on your mom's
not on your
floor.
mother's kitchen floor. She'll kill you. Oops, that's close enough. Anyway, okay. Then I can take this away, and I'll tell you why I used a circular component. Yeah, it does now. You would carry this in, okay, using a ruler, of course. This is all part of the challenge. Remember, I was going to give them a challenge. This is it.
So I'm hoping you guys are paying attention.
So they now all meet. We can use a protractor, and we can now measure these 3 angles. Okay, and once I know those 3 angles, we can actually work out how it works. So what we're going to do, thank you, gentlemen. It's always nice to have friends. Okay, is we're going to take this, and we're going to say to ourselves, okay, here's our 3, and I'm going to translate this piece of paper onto here, okay? So we're going to say, I'm going to leave it there. You don't need to refer to it anymore. And we go, okay, first of all, we're going to draw a free body diagram. Now, free body diagrams are really important for us because they show us the forces coming from the center of the object. Whether it's a round tin like I used, or a person, or an elephant, we have these random questions, or a car, or a box, it doesn't matter because free body diagram says to me, I start with a dot, okay? So here we go, and the beginning of a free body diagram is a dot. So there we go. That represents my object, whatever that object might be. Then, from the center, we always draw the arrows pointing away from the object, never towards it with a free body diagram. So even if we're taking the tin and I'd been pushing and Ty had been pulling, I still have to draw my pushing force away from the object. So it's all about the direction. So now we go, and I've got it in front of me, we go, okay, we had 3 forces. They're all going to start from the center. We're going to say this was Ty. Okay, he went off to one side. Then John, oops, got an extra one there. John went off over there. And I was pulling it over there. My free body diagram. But it's not finished yet because we've always got to label it. We must say what our forces are. Here, be creative in the way you label it. Okay, make sure your examiner or your teacher or whoever's looking at your work knows what you're referring to, because now we just had 3 forces, and if I call each of these F, so I go, this was F, and this was F. Well, yes, we had 3 forces, but there were 3 different forces, and we weren't pulling by the same amount. Okay, you saw that when the tin moved. So sometimes we might have been pulling at the same amount when we managed to keep it nice and stationary. That was great, okay? But then Ty would pull it a little bit more, so we know he's got a bigger force. If I give it the same name, I'm pretty much implying that they're the same. And they don't have the same value. And 2, they're not in the same direction. Direction is part of the value, if you want to think about it like that, of a vector. So I can't say the same. So we can label it force 1, force 2, force 3, but let's be more specific because we know who's pulling what. So we're going to call this force of Ty. Okay, she's famous now. Okay, force of Ty. We're going to call this the force of John because that was his force. And we're going to call this one the force of Tracy. Don't call it force of me. Okay, I know it was you, but your teacher didn't. Okay. And often, you're going to see this in your questions, that you're going to be told that someone is pushing a box or pulling a box. Call it by their name. So we know. Okay. This is now a force diagram. What we would need to do is measure the angles in order to do the vector diagram. In a test or an exam, if they want the force diagram and you're not given the angles, you're just told there are 3 different angles, or you'll see this when we do static and kinetic friction, sometimes you don't know the angle. Then don't add it in. If we go and measure these angles, then draw it in, okay? And this one, we're going to say is actually at 90 degrees. Put it in. Put in the values you know. Makes a huge, huge, huge difference, okay? Very, very important. Now, okay, now we've got the vector diagram. Now life gets interesting because we look at this and we go, okay, I just said to you, let's do head to tail. Great. Scale diagram at this point in time is the only way you can solve this. Okay. Though my challenge to you today, and I'm not going to show you the answer straight away, is, in fact, I'm not going to show you the answer today. My challenge to you, grade 11s, is once I've drawn this vector diagram, and once we have gone through some of the stuff on how to solve using trigonometry, I want you to see if you can solve this using a calculation. Okay? You might not be able to do it today. Keep it in the back of your mind, okay? Keep it there, think about it, and I want you to think about how you could solve this if you weren't allowed to do a scale diagram, okay? In other words, you have to do it by calculation. This is very, very important. We will be doing it in future lessons, but I want to extend you a little bit, okay? So see if you can do that, but let's draw what the vector diagram would be. Now, we would have used the Newton meter, and we can we would have measured how much the force was. So let's just make our lives easier and say, okay, Ty was pulling at 10 newtons, and John was pulling at, let's say, 12 newtons, and I was only pulling, especially that last time we did it, they were pulling harder than I was. I was pulling at, let's make it at 8 newtons. Okay? So, also, in a free body diagram, if you know the values, write the values in, very, very important. This is actually so much easier than it looks. Let's start with Ty, okay? So we start with Ty. He was the first one. He went off at an angle. So let's do his force first, okay? And I'm going to try and keep it in line with the way we drew it. So, and he was going to 10 newtons. If we go 1 centimeter equals 10 newtons, then we can, that's a ridiculously tiny drawing. 1 centimeter equals 1 newton. It's a 10 centimeter line. Very nice. Remember, you don't want to make your diagrams too tiny because then they can't be accurate enough. The bigger they are, the more accurate they are. But there's a limit on your page, okay? So, Ty went off in that direction, okay? Then remember, I said to you, let's just extend a little bit. So now we can do John, who, if we look back here, was at 90 degrees to Ty. So John's force comes from here, and he's at 90 degrees, so and he was a little bit smaller, so it's there, okay? This being 90 degrees, which means that's also 90 degrees, remember? Ooh, doesn't like the blue, because they're 180 degrees. Now, we do have a little piece of information missing because I didn't tell you what angle it was, and the way I've drawn it, it pretty much looks like this is going to be 135. Okay, that's what it sort of looks like, so let's just say it is. Now watch, this is the third one that we need to do. It's at 135 degrees to John. So, just like we did with Ty, I'm going to extend this a little bit. We measure 135 degrees, okay, and now things get complicated because I'm going to measure it from here. So I measure 135, so there's 180. No. Can I? It's a good thing I know how the values work on it. Seriously, not 180. Anyway, moving on. Okay. This is what I'm trying to tell you. When this line has to come here, okay? So watch. I do this. We say this is going to go down here because that's where it's like I've moved it across here. The 135 is here from the top. It's always from the head, okay? Not from the funny side of it. So I measure 135. That was interesting. Measure 135 degrees, okay? So it's round about like that. And then I'm going to draw in my force. And mine was the smallest, so it's about there, okay? Let's just move this over so it actually is on the arrow. There we go. And that was mine. Okay? We're okay with this because we realize, and let's just put in what we know, this was 135 degrees over here. That was 90. This is Ty's force. Now, I couldn't just call Ty's force F of T because mine is also F of T because we both start with a T. So that's why I'm naming them. This was John. And this was me. And you know what? My resultant is over here. So let's make it green because that's nice and bright. The resultant goes to there. And it goes towards the direction John and Ty were pulling in, which is what we expected because they've got a bigger force than me. And we would then measure. So this is my resultant force. You measure it with a ruler from beginning to end, and then we can measure this angle, and we know which angle they would go in, okay? I'm not going to tell you what that answer is, because this is something, well, I made up the numbers anyway, and we couldn't measure what we were doing, but it's a very, very important skill, okay? And in fact, we could do this with an infinite number of forces on one object if we really wanted to, but nice thing is they're not going to, okay? This is about as complicated as it's going to get. But I'm challenging you again to find a way to do this without having to do the diagram, because the diagram takes a long time. Didn't take us that long, because I'm not being accurate. I'm not actually drawing the line to the right length. I'm not drawing the angles to the right angle. But you need to do that. You need to spend time doing it. It is a skill, grade 11s, and you need to practice that skill. Okay, so it's practice, practice, practice. So the vector diagram is really important, and remember, you've got to be able to do it from a force diagram. And time for a break.
Alrighty, so mindsetters, don't disappear. I am so busy since I've gotten up from the floor there, like my knees are still dying, but I'm frantically on the page, so mindsetters, keep on posting, keep on posting. You're making my job worth it. See you after this break. And welcome back, mindsetters. I hope you're now refreshed, you're back, you're ready, you're focused, you've done whatever you had to do, you're here, you got your juice, you went to the bathroom, now you're focused, paying attention with your pens, pads, and your phones out. Remember the 3 Ps. Now make sure you get on the page, chat to me, but don't forget to make notes, because that's why we're doing this, so you guys can learn. And you don't learn without making notes, can you?
No, you can't.
But yes, so pay attention, because I'm going to hand it over to Tracy. Tracy, take it away.
Oh, thank you, Ty. Okay, so let's get on to what happens when we can use a calculator, which I have to be honest, I prefer. I don't like scale diagrams. I don't have enough patience. So, says to us, James exerts a force of 12 newtons on a box placed on a horizontal frictionless surface. Okay, so let's draw a picture of what's going on, because that always helps. So James, we have a box. He exerts a force of 12 newtons. Let's just say he's going this way. There's my 12 newtons. This diagram at the moment is for me. Okay, this is for me to know what's going on. And at the same time, Precious, should be capital letter, exerts a force of 5 newtons at an angle of 90 degrees to the box. So Precious exerts a force of 90 degrees. So now it doesn't tell you whether the force is up or down. Okay, so let's say she pushes upwards. Okay, let's just make it a bit easier. So now she's pushing on the box at 90 degrees with 5 newtons. So it's at 90 degrees. So that's a force diagram, basically. If we had to draw this as a free body diagram, just including the forces that Precious and James exerting on the box. So what we have there is James is going in that direction, and Precious is going in that direction. So there's my 5 newtons. Let's make it so that you can read it. 5 newtons, and there's my 12 newtons. And we go, okay, big NB in the way this is asked. It says to us, calculate the magnitude and direction of the resultant force. Guys, please be careful. In your exams, particularly at the end of next year in grade 12, if they say to you calculate and you do a scale diagram, you don't get any marks for that because you haven't answered the question using the method they told you to. Calculate means calculation. Okay? If they said determine the magnitude and direction, then it doesn't matter. You can do it however you like. We're going to do it the way they want, which is by calculation. Okay? So, that means we need a diagram that we can use. So we're going to change this into a vector diagram. It's not a scale vector diagram, but it's one we can use, and we're going to draw it head to tail. So all of this stuff in green was for me. Okay, now we start. Okay, now I'm doing my calculation, and we say, fine, James went off in that direction, so let's call this the force of James. I've only got James and Precious, so I'm going to use a J and a B, and James had a force of 12 newtons. Precious went up here, let's call it the force of precious, which is 5 newtons. So my resultant is from the beginning of James to the end of precious. Still do this with the ruler so it looks nice and neat. And there's my resultant. Okay? Now we look at this and we go, we can do this because that was at 90 degrees. You know this. You've done this since last year. You did trigonometry. You did Pythagoras in grade 10. So we go, yay, easy. Let's ignore the angle for now because we are going to need to know what this angle is. Let's work out FR. And we go, well, it's a right angle triangle. It's a really badly drawn right angle triangle, but it's a right angle triangle. And we're actually looking for the hypotenuse. So we remember Pythagoras' theorem says to us that the square of the hypotenuse is equal to the sum of the square of the opposite two sides. Something to that effect. Okay, it's been a while since I taught maths. Which means, please watch how I set it out, grade 11s. This is important. My hypotenuse, which is FR, is equal to James's force squared plus Precious's force squared. Okay, that means we've got 12 squared plus 5 squared. We take out our calculators, okay? That gives me 144 plus 25. So the square of the resultant force is 169. I don't want the square. I need to square root it. So we say, okay, that means that my resultant force is 13 newtons. But I haven't finished because the question was magnitude, done, and direction. Okay, not using a protractor. Go back to our diagram. Okay, so we know that this is now 13 newtons. Grade 11s, you can now use any of your trig functions, sine, cos, or tan. I'm going to say to you, as a tip, don't use sine or cos, because sine or cos require you to use the hypotenuse, the 13 that you've just worked out. If your 13 is wrong, which we know it's not, but if it's wrong, then you're going to get the angle wrong too. And carry-down errors are horrible. You don't want to have a carry-down error. So let's not have a carry-down error, okay? So let's use tan. Watch again, and now we've got to remember, tan is opposite over hypotenuse. So tan means, tan theta for this one is going to be the opposite side, which is precious, divided by James's force. Please be careful about using your maths lingo here and making it x over y or y over x or whatever it is, simply because there is no x or y on your diagram, and sometimes you guys forget to put a diagram because you drew it on your question paper, and then we don't know what you're referring to, and then we can't give you marks if you go wrong. Okay, so that means it's going to be tan theta equals 5 divided by 12. Now, we need theta. Now, I want to show you how to do this on your calculator just in case you've forgotten. And we can do this in one step. So we do second function tan, because we're looking for the angle. Okay, so we arc tanning. Then we're going to go 5 divided by 12, and close your brackets, please. Okay, so the calculator knows that was the one that we wanted. And we go equal to, and we get 22,62 degrees. Remember, we've got to round it off to 2 decimal places no matter what. So 22,62. So this is, let's do one more step. So theta equals 22, what was it? 62, hey? There we go. 62 degrees. Okay? I know the magnitude, I know the direction, but I have to put it together. These are all separate, and they're all nice calculations. So what does that mean? So then we go, therefore, my resultant force is 13 newtons at 22.62 degrees from the force of J. Okay? Or because James was horizontal, you could have said it's 13 degrees, at 22.6 degrees from the horizontal. Okay? But it's from James. This is where the 22.62 degrees goes in. Okay? So remember, force is a vector, which means when I want the whole force, I've got to give the magnitude and direction as one thing, not in two separate answers. So we write it out. It's almost like answering a word sum in maths where you have to answer a word sum with a sentence. Same thing. Okay, so time to mull that over a little bit. So time, we're going to take a break, I think, and then I've got one more question to challenge them a little bit with.
Okay. So, mindset as you heard the lady. Don't disappear now, because you're going to miss out on the challenge. And what's the point in your brain being there if you don't challenge it once in a while? So make sure you stick around. Do not go anywhere. We'll see you after this break. And welcome back, Mindsetters. Hope you had a nice little break there. You went and did whatever you had to do. You got some juice. You just got back into the zone. So now make sure you're focused, pens, pads out, and phones. Get on the page. Chat to me. Let me know what you guys are thinking because we're running out of time. So we're gonna give it to Tracy straight away.
Thank you. Okay, Tash, we answer that question quickly.
Yes, a
Let's
question
do the
actually
question.
came in from Matiso and Lucinda. Sorry, I always. Just you need to tell me how it's spelled or said. So, yes, she says, my teacher told me that we cannot use tail-to-tail method if we have three forces. Why is that so? Because she's confused.
Okay, Sweet Pea, first of all, I'm not going to try to pronounce your name because I'll butcher it more than he did.
Yeah, we're going to call him Mats.
Yeah.
Mats.
What your teacher's saying to you is tail-to-tail, which we haven't done, cannot be done with three forces, okay? Head-to-tail can, like I've done, but what your teacher's telling you is more than likely, and this was the challenge I gave you, is when you've got three forces, you're going to be asked to do it by calculation. Okay, and when we get to components, we're going to show you how to do that. So tail to tail absolutely cannot be done with three forces because it results in a parallelogram, which if you've got three, you can't draw. Head to tail, absolutely you can do millions head to tail. Okay, but your teacher's trying to get you to the point where you realize that once there's three forces, you're more likely going to be asked to do it by calculation using components. Okay, so tail to tail, absolutely not. Head to tail, go for it. It's the same thing, but probably going to get asked to do it by calculation. Okay, so that's where your teachers are coming from. It all depends. Also depends on which textbook they're using. Some textbooks are more prescriptive than others as to how to do it, okay? And it's a new section to this curriculum, so teachers are still trying to find their way, okay? But hang in there, okay? Now, what we have here is, and we're going to fly through this one, a metal rod with a mass of 150 kilograms. So let's write it into here so I remember. So that's 150 kilograms. Is suspended by cables on a construction site as shown in the sketch. That means it's not moving, okay? So let's just think about this. Cable B is going to be pulling in that direction. Cable A is going to be pulling it in that direction. Why must they be pulling it up? Because it has weight. So gravity acts there. And before I've even done the first question, I've already answered it. Because it says, draw a free body diagram to show all the forces acting on the metal rod. So we've actually just done that. Can you see? By putting those arrows in, I have my free body diagram. So that means over here, we have FG. That's the force of cable A, so I'm going to call it force A. That's the force of cable B. And over there, that is 100. Ooh, let's make it so you can read it. That is 135 degrees, and that's force B. Free body diagram, done. Okay. Then they say to us, wrong way, that, so we got the same thing, and it says, draw a sketch to show the resultant of the forces acting on the rod if cable A breaks. So, this is acting straight down like that. That's 135 degrees, And now we've got to go, okay, we actually needed slightly more information. What this didn't tell you is that this is at 90 degrees to the wall, okay, because it needs to be, otherwise we can't answer this question. And in fact, the resultant, and this is a little bit of trick for you to remember, is going to be in the same direction that cable A is in. Because if it isn't, then cable A is not doing any work. So the resultant, we would go, okay, cable B is in this direction, so that's force of B. There's FG, because it acts down, so we're doing head to tail. And there's my resultant. So that's how, ooh, that is theta. That's how I would get my resultant, okay? Ooh, and I'm going to have to rush. I'm going to leave this for you, actually, this last part, because now it says, if the tension in cable B is 2,500 newtons, calculate the mass. I'm going to go back here. Okay, calculate what that is. Okay, this was 2,500 newtons. You know where the trick is? Fg, right here. Because Fg is mass times gravity, so that's 150 times 9,8, which I'm going to leave you to work out because I've run out of time, and you can calculate this the way we've done it. Pythagoras, okay, because you'll have found this is a funny number. I'm telling you now, it's got decimal points in it, perfectly okay, and then work out theta using tan. Okay, and I've run out of time, as usual. Always so much to say.
So much. But mindsetters, I hope you've had fun. And as I said, if you guys are looking for notes, make sure you go to www.mindset.co.za/learn/extra/live. Do yourself a favor, go there, help yourself out, check out the new updated pages, you know. So we made it so we could help you guys out. So we're like, you know what, you must just use it. Don't just look at it, just use it. There you can download all your notes and everything. But for me, this is where I sign off and say, see you next time.